let's take a quick jump back to chapter 6. I know I said we'd be going through that. We're not like going through chapter 6 as a chapter. We're not doing homework in chapter 6. There's just a few definitions you need to know because they'll come up again as we go forward in the next chapters. So we just need to know what each other are talking about, and so we can apply that later. When you go into the second semester of chemistry, whether it's 122 here or wherever you end up taking it, then you'll talk about thermodynamics at length, and so we don't need to spend quite as much time on that here. But let's talk about our basic definitions, because these are some words that we use a lot, we don't necessarily think about. So what is energy? Do we know how we define energy? I mean, you've probably heard that term before, right? So what is it? Something that everyone has a lot of right now, clearly.
I don't know.
Yeah, and something.
It's something that's
The magical force. What?
It doesn't have mass. You know that.
Doesn't have mass. It's defined as the capacity to do work. What is work? Yeah, it's applying a force over a distance. So if I lift up this book, I'm applying a force against the force of gravity, pushing this book up. That's an example of work. And I had to do something with energy to do that. So what did I do with energy to push this book up? Is it like you have to get rid of the energy to do it, or what's happening there? So the book's here, I apply a force over a distance, so I do work. What happens to the energy that I used to do that? Yeah. Yeah, well, how is it changing forms? The other one, potential. Yeah, so that's part of it. Is while the book is moving, we call that potential energy, the energy of motion. And then is there a difference between the energy of the book here and the energy of the book here? I'm seeing some head nods. Yeah, why? What's the difference? Yeah, that change in height means is this book have more energy or less energy than down? If it's up here, does it have more energy or less energy? It has more potential energy, because if I drop it, it'll go down. Right? So I've transferred energy from myself to the book by doing work to it like this. And that's kind of the classic physics definition of transferring energy via work. So there are two ways to transfer energy. One is to do work, so to apply that force to the distance, and then you've transferred the energy to something else. What's the other way to transfer energy called? It's more applicable to chemistry. So like you could talk about chemical reactions doing work, like producing gas at a pressure that then pushes something out. But more often we talk about the energy of chemical reactions using this other quantity. Any guesses as to what it might be? Heat, yeah. So heat is another way to transfer energy. In fact, heat is a direct transfer of energy that doesn't involve work. So we talk about two ways of defining energy, or defining energy transfer. We talk about the system, and we talk about the surroundings. system is what we're interested in or focused on. And the surroundings is everything else, and really everything else. So let's go back to the book example. I transfer energy by doing work by moving the book up. So let's say the book is our system. Is that a positive transfer of energy or a negative transfer of energy? If the book is the system, is the book gaining energy or losing energy? It's gaining energy. So that's a positive energy transfer from the standpoint of the book. But that's an arbitrary distinction. If I'm the system, what's the difference there? Then it's the opposite, right? If I'm the system, then I'm losing energy to the book. And so now the energy, the sign of the energy transfer is going to be negative. So the sign of the work is either positive or negative, depending on that system and surroundings. All right, so let's get out of books here and talk about the chemicals. So there's kind of a neat graph or a little picture from the book. We won't put it in the notes, but we can just look at it. You can think of the energies of the system and the surroundings always having to add up to the same thing, because that's the law of conservation of energy. Energy can't be created or destroyed. So if the system has a certain amount of energy and the surroundings has a certain amount of energy, and then they transfer, the surroundings are going to gain the same amount lost by the system, and so on. So what does that mean for chemistry? What do you think in a chemical reaction, what do we define as the system? If you were a guess. So you're doing a chemical reaction, you want to know which direction the energy is traveling. What do you think we define as the system? The reactants. The reactants, right. So for chemistry, or we can be more general, we're going to define that system as the chemical compounds participating in the reaction. So then what's the surroundings? Everything else. So that means, and the reason we're kind of going through this slowly like this, even though surroundings are just everything else, but it's also everything else that's right in contact with those chemicals. So remember, when you do a chemical reaction, it's usually not like the pure chemicals just mixing together. They're usually in a solution, right? Like you dissolve it in some water and you mix them together and they do something. So the solvent, the glassware, that's all part of the surroundings. It's only the actual chemicals themselves that we define as the system. All right, so where does that get confusing, or where does that get, where does this become important? We're going to define two terms that you've probably heard before. Maybe. Well, hold on. Let's define one more term first, and then we'll get to that. Okay. We're going to define. All right. We're going to define this term enthalpy. Okay. Have you heard this term before? Maybe. Its symbol is H, And we usually define it as, we don't have to go through the whole derivation, but basically it's the heat transferred in a chemical reaction. So it's like the heat, so the total energy is always the heat and the work together. So that's the two ways to transfer energy. The enthalpy is taking the heat out of that and talking about just the, or taking the work out of that and talking about just the energy change due to heat. So energy change due to heat. If the pressure changes, then it gets more complicated and enthalpy has to take pressure into account. But we can generally talk about this as just the energy. So when we talk about the energy change in a reaction, we often talk about the delta H, which is technically the change in enthalpy but it's kind of a stand-in for just general energy. So you'll see it used describing chemical reactions. Technically, there's other variables. When you get into thermodynamics, you'll talk about free energy, which is delta G, and you'll talk about total internal energy, which is delta U, and there's all this other stuff. But for our purposes, for chemical reactions, most of that change is usually heat. So we can just shorten it all up and say, okay, we're going to talk about this enthalpy, and we just mean heat. It's convenient also because it's H. Does anybody know what the variable is for heat itself, like pure just heat? It's not H. Yeah, it's Q. So it makes more sense for it to be H, right?
Weird.
All right. So we can talk about the change in enthalpy of a chemical reaction. How does the heat flow in a chemical reaction? So let's look at one. Let's look at one that we know. All right, so here's combustion of methane, like natural gas, like our Bunsen burners. Okay, they're combusting. So what's happening with the heat in that reaction? In other words, how would you describe how the heat is transferring? Where is it coming from and where is it going to?
It's losing heat.
What's losing heat?
It's an exothermic reaction. So giving off heat.
It's giving off heat. Would everybody agree that when you burn natural gas in a Bunsen burner, it gives off heat?
Yeah.
All right. So it's giving off heat. So what does that tell us about the direction of energy transfer?
It's one way.
And from where to where?
Reacts to products.
Kind of. It's not exactly reactants to products. It's from the system to the surroundings. So another way that we could write this reaction is actually putting the heat in as a product. So the energy is transferred from the potential energy of the CH and OO bonds on the left and is turned into heat, which makes it hot. So what's our sign of delta H? Is delta H going to be negative or positive here? Negative, why?
Negative. I said positive. I don't know what.
You said positive?
I said positive.
I heard negative. It is negative.
You say okay.
So we'll stick with that. Yeah.
It would be negative because it's losing the energy to heat it.
Right. So remember that the reactants or the molecules are our system. That's what's losing the energy. So it's losing energy. So that means it's going from a high energy state to a low energy state and shooting out the rest of the energy as heat. And that tells us that there's a negative overall enthalpy. So the products are at a lower energy than the reactants. The name for this type of a situation is exothermic. Exothermic means the enthalpy is negative, meaning that the energy is being transferred from the reactants or from the molecules from the system out to the surroundings. Okay, so here's where this sometimes becomes confusing. Let's say we do another reaction, another exothermic reaction, and we do it in a test tube. So like you put some solid solutions together, mix it up, and it gets hot. So if it gets hot, doesn't that mean that heat is going into it? If the temperature goes up, doesn't that mean that the heat is going in? It doesn't, but why not? The temperature is going up, right? You put your two solutions in a test tube, you mix them up, you measure the temperature before and after, the temperature has gone up.
Is it some of a closed system?
What?
It's like a very closed system or something?
Well, yeah, so we have to think about where the energy is coming from and where it is going to. It's true that it's getting hot, but it's not getting hot because heat from the surroundings is going in and making it hot. It's because heat from the system, the actual molecules, is heating up the water and the test tube and making it hot. So the heat is going out, it's exothermic, but the temperature is going up, which sometimes confuses us. So if you always think about that language of system and surroundings, and think about the actual molecules, the actual little things that are reacting are the system, then that should help to keep it straight. So what's the opposite of an exothermic reaction? Yeah, an endothermic reaction. Here's an example of that. Methane gas in the ground is compressed to become solid carbon, graphite, and hydrogen gas. And so that is not obvious, but that is going to have a positive enthalpy, and we call something with a positive enthalpy endothermic. So that means it takes in energy. Okay. So that's basically all we have to talk about from chapter 6. If you want to know more about how you actually calculate these things, you can do that. It's pretty simple. All you do really is you take the energies from one side and the energies from the other side, and you add them together. Just got to keep your signs right. But let's practice a couple little problems. So that we can practice this and see how this might come up on a quiz or an exam, because we're not going to do homework from this chapter, but just something like this. So we've got 4 things described here, and the question is, which process is endothermic? Evaporation of water from the skin, burning of candle wax, oxidation of iron, combustion of natural gas. Now, there's one little problem with this question in that it doesn't specify what the system is and what the surroundings are. Really should do that. So we're going to assume that whatever they talk about, whatever they're focusing on in the process is the system. So when they say the evaporation of water, we're going to assume that's the system. When they say the burning of candle wax, assume that's the system. So go through each of these and see if you can find which one would be endothermic. Which one is the energy transfer positive? So energy is going into the system from the surroundings instead of out of the system. Everybody got one? Which one are you thinking? C is endothermic? How do you know?
Oxidation.
Oxidation is always endothermic?
Because all the other ones, something's going away.
What's going away?
Like the evaporation of water from your skin.
Okay.
Like losing water.
Okay, but let's focus it just on the heat. So let's talk about number C, or letter C. The oxidation of iron in a chemical hand warmer. What's a chemical hand warmer? Have you ever
No.
used those, seen those? So that's not a great question, but it's not a common reference. But can somebody explain what that does? People who have that. But
It's like a bag you crush and then, not crush, but you kind of like break a little bit and then
yeah,
it gets hot.
it gets hot. Okay, so there's your clue right there. It gets hot. What does that tell us about the direction of energy transfer in that reaction? Yeah, it's losing heat. So the chemicals or the system must be losing heat to the surroundings being your hand. So it's warming up your hand. So the energy is going out, so that's exothermic. So that one's not endothermic, that one's exothermic. And the key there is thinking about which direction the heat is transferring. What about B and D? Yeah, those are pretty clearly exothermic, so it's got to be A, right? How is evaporation endothermic?
Another means going to the system, right?
Endothermic means the energy is going to the system, that's correct. So is that what happens in evaporation? It is, right? Gases, like water vapor, is a higher energy than liquid water. It requires energy to break up the intermolecular forces in water to make water vapor. So that's an example of an endothermic process. The other clue there is, what's an example of evaporation of water from the skin? When does that happen?
Like sweat.
When you sweat. And what does sweating do to you? It cools you off. So that's another example of where the energy transfer is going. The energy or the heat is going from your skin into the water, and that's why it cools you off. You're losing the heat. The heat is transferring from your skin to the water. Okay, let's look at another one. Part of this is kind of one we already did, but I guess that's a really common example. So identify each energy exchange as primarily heat or work and determine whether the sign is positive or negative. Yeah.
I have a quick question about the last one.
Yeah.
With like candle, or like candle wax burning.
Yeah.
When like the heat is leaving, right? Is that like the molecules of like the candle wax? Wouldn't it like be going back into the candle wax and then like burning it more or whatever, something like process?
Sure.
Why would that not like be considered like heat?
I guess the answer is that there's more than one thing going on. So when you're burning candle wax, that's a combustion reaction of a hydrocarbon. Candle wax is a hydrocarbon. So it's very similar to the methane reaction. So that reaction itself is producing a lot of heat. Most of that heat is going out to all of the heat is going out to the surroundings. But the surroundings include unreacted candle wax, which is, I think, kind of what you're talking about, right? Because the candle melts. If it's combusting, it shouldn't be melting, it should just disappear. And so, yeah, so the surrounding from the actual molecules that are reacting at any given point includes the air, it includes the wick, it includes other candle wax. But we have to focus on what is the actual chemical process that's going on. Yeah. If it said the melting of candle wax, that would be different, and that would be an endothermic process. But you're right, so on balance, more energy is being released than is going in to melt the candle wax. Otherwise, it wouldn't seem hot. But those things are going on together. Okay, so we talked about A being, so we talked about that as exothermic or endothermic. How do we define it in this situation where it asks for what is the sign of the energy change? Is it positive or negative in A? It's positive because the energy is going into the system. So the system is starting at a lower energy, ending at a higher energy. The sweat is starting at liquid, ending at gas. So it's gained energy to do that. So that's a positive change in energy. And is that heat or work? That's heat, yeah. So what about B? A balloon expands against an external pressure. The contents of the balloon is the system. So first of all, is that heat or work? That's work because it's pushing something. It's not changing temperature. It's pushing, or it's pushing against that external pressure. So is the balloon doing, or is the air inside the balloon doing the work, or is the work being done to the air in the balloon? Why? This one's a tricky one, and it's not super applicable to us, but it's actually that the contents of the balloon are doing the work. So if we think about the balloon as like the shell of it, then yes, that's being pushed on, but it's the contents that are actually doing the work. So that would make this a negative energy change. And then C, this is more important to our purposes. An aqueous chemical reaction mixture is warmed with an external flame. So the reaction mixture is the system. Is that heat or work? Should be pretty obvious. It's heat, right? It's warmed. Okay, so is the sign positive or negative? Positive, yeah, why?
Because the reaction's gaining heat.
Yeah, they're gaining energy, so they're going from a lower temperature to a higher temperature, so that's a positive change in energy. And would that be called endothermic or exothermic? Yeah, endothermic. Endothermic, endo means in, and exo means out. So an endothermic reaction, the energy is going into the system. All right, so that's all you need to know about heat. Just be aware that that delta H thing means enthalpy, that chemical reactions can both absorb heat or give off heat, and those terms are endothermic or exothermic, and those are associated with positive and negative enthalpy changes, respectively. All right, enough about heat. Let's get back to some molecules. So if you remember, back last time, open those notes up so we can review. Talked about all that weird quantum mechanics stuff. But one of the important things that we kind of settled on at the very end was we talked about these 4 quantum numbers. I know it's small. I just wanted to put it all on the screen so we could talk about it. NL, ML, and MS. And we did some practice with assigning NL and ML and which numbers you can or can't have. So now we're going to talk about the consequences of that and how we can explain all kinds of periodic properties, like what atoms do, just based on knowing these things about their electrons. So first of all, we have to know about this last one that we haven't really talked about, which is called electron spin. That was that last quantum number, that MS. And we said that that could be either plus or minus 1/2. So the term that's given to this is electron spin. And sometimes we say spin up or spin down. And the idea is that any kind of rotating charge is going to create a magnetic field. What's the name of that? I can't remember. Any physics folks in here? Induction, right?
That's that's electron. That's electricity through magnetic field.
Right. Yeah. Okay. Yeah. Induction. Right. So it was thought originally that electrons would do that, and if they were spinning one way, their magnetic field would be going one way. If they were spinning the other way, the magnetic field would be going the other way. Because in fact, they do line up with magnetic fields in that way. Now we know it's a little more complicated than that. So spin is just kind of like an internal property, like it's a thing that they have. But what we're going to talk about with this, ms is either plus 1/2 or minus 1/2. And there's something called the Pauli exclusion principle. And when we name it or when we write it, it doesn't seem to be all that interesting in terms of its consequences. But when we look at what that actually means, it's kind of a big deal. So the Pauli exclusion principle just says no 2 electrons in an atom can have the same 4 quantum numbers. No 2 electrons in an atom can have the same 4 quantum numbers. So if we take an atom like hydrogen, how many electrons does hydrogen have? 1. Is this important for hydrogen? Not so much, because there's just 1 electron. So hydrogen has 1 electron, and what are the quantum numbers in hydrogen's electron? That's N. I'll give you a hint. It's the lowest one possible. What's the lowest value N can have?
0.
Close. 1. So N is 1. L has to be 0 because the largest it can be is N minus 1. Then ML, 0. And so that's what we did last time. So now we can add this 4th quantum number and say that ms is 1/2, plus 1/2. Now it could be plus 1/2 or minus 1/2. By convention, we always do the plus first. And so that's the 4 quantum numbers that hydrogen's electron has. Now let's move to helium. How many electrons does helium have?
2.
So helium has 2 electrons, 1 and 2. And we know that first electron is always going to have that same base set of quantum numbers, 1, 0, 0, plus 1/2.
Do you remember what those first 3 are?
N is the principal quantum number, L is the angular momentum quantum number, and ML is called the magnetic quantum number.
Okay.
They're defined by each other. So N is the first energy level, the first shell, sometimes we talk about, and L tells us the type of orbital, so S, P, D, F, and then ML tells us about the orientation of that orbital. All right, so we've got those four quantum numbers for the first electron. How can the second electron have not the same 4 quantum numbers? Or in other words, what would we change so that it fulfills the Pauli exclusion principle? What? MS. Why would we change MS and not the other ones? What? They do stay the same, but why? Why couldn't we just say that the second one goes in the n equals 2 instead of the n equals 1? Ideas? Think about the stuff we did in the last chapter. What happens when electrons move from shell to shell, to different n levels?
They gain energy.
Yeah, they gain energy. That was the whole thing about the flame tests and the lamps, right? The electrons are promoted to higher energy levels, and then they relax back down and give out light. So if we were to have electrons in higher energy levels, those would be what we call excited states, meaning higher energy. So it takes more energy. We know everything likes to tend toward the lowest possible energy. So the lowest possible energy that that second electron can have is to still be in the n equals 1 shell, still the L equals 0 subshell, still ML equals 0 orbital. And because we have to fulfill that principle above, then this electron must have -1/2 for its spin. Okay, so let's jump up to the next one now. Lithium's next. How many electrons does lithium have? 3. So let's list the 3 here. And we want to always have the lowest possible energy first, because electrons want to have as low energy as possible. So that means these first two are going to be the same. And what about that third one?
Put NV2.
Why 2?
Because it's like the first thing on the list that's you can move up. I don't know why.
Right, you're right. So if we look at all those numbers, it would be great if that electron could stay in the n equals 1 level, because that would be lower energy. But there's no way for that to happen, because if it stays in the n equals 1 level, let's try it and see. If we want it to stay in the n equals 1 level, then what choices do we have for what L can be? It has to be 0, because L can only go from 0 to n minus 1. So L has to be 0. What choices do we have for ML? Do you remember? It's also got to be 0, because ML can only go from -L to +L. So if L is 0, there's only one ML, which is also 0. If L were 1, then we could go -1, 0, or 1, but we can only go 0 there. So then MS has to be either +1/2 or -1/2. Either way, we conflict with the other electrons and we violate the exclusion principle. So that tells us that it's not possible to have another electron in the n equals 1 level, because it would have to have the same 4 quantum numbers as another electron. So that tells us our third electron has to go up to the n equals 2 level. And now we've got some choices. What are the possible L values for n equals 2? 1 and 0. So which one are we going to pick for that first electron, for that third electron? If you were to guess, what do you think? Maybe 1, maybe 0. Could go either way. Well, we're going to stick with this idea that the electrons are at their happiest or their lowest energy when they have the lowest values. And in fact, the L equals 0 level, which is an s orbital, that spherical orbital, has a lower energy than L equals 2, which is, or L equals 1, which is the p orbitals. We'll talk about why that is in a minute. So that means ML has to be 0, and then MS can either be plus or minus 1/2. We usually stick with the plus first. So we can start building up these electron configurations by thinking about how they can have the lowest possible quantum numbers without violating the Pauli exclusion principle. But doing this is a little bit tedious, and always thinking about the quantum numbers every time is not something we're going to do when we get up into big multi-electron atoms. So let's introduce a little bit of a shortcut here and talk about what we're going to do with that. There's a couple ways you can do this. The way they do it in the book is with these boxes, so we'll stick with that. Oh, okay. Got it in here. Another way we could write lithium, the electron configuration for lithium, is to say it's going to have some electrons in the first quantum level, draw a little box, and we're going to call that the 1s orbital, which is exactly the same thing as talking about these quantum numbers. Because we know it's 1 from the n equals 1 quantum number. We know it's s from the L equals 0 quantum number, because 0 goes with s, 1 goes with p, 2 goes with d, and so on. And so what kind of an orbital does that make this one then? What would we call that orbital? (2s), yeah, thanks. So that's a 2s orbital because it's n equals 2 and L equals 0. So we would say we have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. And the ways we can write that are, one common way to do it is to draw little arrows up and down like this to indicate the different spins. So that would be our 1s. This would be our 2s. So there's 1 electron in the 2s. And then the other way, and the way that we ultimately want to do it, is something called an electron configuration. It looks like this. Where we just write them sequentially with little superscripts indicating how many electrons are in each orbital. So there's 2 electrons in the 2s and in the 1s and 1 electron in the 2s. So this thing is called an electron configuration. Next one. So I thought today we could just go through and do all 118 of these. We'll just do them one by one, and they'll be fun, right? Probably not. So we won't do that. But we'll do a couple, and then we'll jump to where it gets a little tricky. Oh, yeah. All right. Good. So if we jump to beryllium, we now have 4 electrons to deal with. Where do they go? The first 2 are going to go in the 1s. Yeah, so we've got the same as lithium. We add 1 more. We have space for it, and the little box way of doing it shows pretty clearly that there's space for that second electron. And then we can write an electron configuration for that as well, which would be 1s2, 2s2. Let's jump back up for a second. So this tells us that one of the consequences of the Pauli exclusion principle is that each orbital can contain no more than 2 electrons. Because if it had more than 2, there would have to be 2 electrons that had the same set of quantum numbers, the same set of all 4 quantum numbers. So that's a consequence of that, and that's why we can make these nice little arrow pairs to do the electron configuration. All right, so we move to boron. We now have 5 electrons. Where do they go? We'll assume that we're going to keep going the same way. Where does that 5th electron go? Yeah, the p orbital. So now we've exhausted the possibilities for quantum numbers for n equals 2 and L equals 0. But in the n equals 2 shell, we have another choice for L. We have L equals 1. So that's what we call the p orbitals. How many p orbitals are there? Not quite. How many orbitals are there? There's 3. How do we know that there's 3? Yeah, but how do you know there's 3 p orbitals? Just the p orbitals. I'll give you hints from the quantum numbers. So let's review from last time. What's the value of L if we're talking about p orbitals? L is 1. So what are the possible values for ML?
0, 1.
Yeah, -1, 0, and 1. So that means if you have an L equals 1, which is your p orbitals, there are 3 different possible MLs, and that's your 3 different p orbitals. So this diagram that we're doing now, this is commonly done in chemistry, but really what we're doing is just talking about the quantum numbers in a graphical way. So we've got 3 different p orbitals. We call that the 2p. And since there's only one more electron to go here, we put it wherever in front there. So the electron configuration for boron then is 1s2, 2s2, 2p1. We're going to do one more, and then we're just going to start jumping around and trying some different stuff. Carbon. Six electrons. So we can assume that everything's going to be the same from before. And then we have to figure out where to put that 6th electron. There's our 5 that we had before. So where does the 6th one go? Does it pair up, or does it go into an empty orbital? Empty orbital. Why? Anybody know why that might be? Why would we give it a different L quantum number rather than the same?
They're negatively charged. They're both negatively charged, and they can only be as far away from each other as possible.
Yeah, there's a energy cost associated with pairing electrons. Let's point this out. We always want to keep the maximum number of unpaired electrons that we can within the same energy. So one drawback of doing it like this with these little boxes is we don't get a sense of where the energies are. So let's grab a graph from the book so we can see that. This is, if you have your own, if you're looking at the book, this is page 343. There are a couple of problems with this diagram, but for our purposes, they'll work out at first anyway. We're just going to pick the bottom because the top is where it starts to have some problems. If we imagine the energy levels of these different orbitals, the 1s is at a much lower energy, so lower potential energy. 2s is a little bit higher. 2p is a little bit higher, but all the 3 orbitals in the 2p, regardless of their orientation, are at the same energy. Okay? The word for that is degenerate. All at the same energy. Since they're all at the same energy, there's no energy cost problem with moving electrons to one or the other, so it's controlled by the pairing. So if we can spread the electrons out, then there's the least amount of pairing energy cost there. So they could be at the lowest possible energy. But we wouldn't want to drop electrons down or raise electrons up to a n equals 3 level or something, because then you're talking about a lot more energy that's required to do that. Okay, so that's the basic idea of how you figure out electron configurations. And if we were to draw this, we would say 1s2, 2s2, 2p2. Let's look at why that is. So why do you think the 1s orbital is a lower energy for electron to be in than a 2s orbital? Where does that come from? And then why are the 2p orbitals even higher in energy than the 2s? Why should the orbitals all be the same energy? What's going on there? What's affecting that? What? The distance from the nucleus? Yeah, that's true. That's correct. So what is it? Why? What does the distance from the nucleus have to do with that?
It changes in angular momentum.
It changes in angular momentum. Well, that's what the L is differences in angular momentum, yes.
So we showed in chapter 7 that the farther we are from the nucleus, the higher energy you need to be.
Yeah, but what's causing that? So yes, the ones closer to the nucleus are lower energy. Why? What's in the nucleus? Positive charges. So how does that work?
There's higher attraction.
Yeah, so we're just talking about positive and negative attraction. It's technical term for it is the Coulombic force, but positive and negative charges attract each other. And the closer they are to each other, the stronger that attraction is. So the attraction is inversely proportional to the distance. So the closer something is to the nucleus, the more tightly it's going to be held, the stronger the electrostatic interaction and the lower energy for the electrons. When we get into the periodic table part, we're going to start talking about the effective nuclear charge, which is a little bit different. All right, so let's try this. Write electron configurations for the following atoms. Okay, a couple straightforward, and then I've thrown in a couple ions. See if you can figure out what happens when there's an ion instead of a neutral atom. You can use the boxes, you can use the levels, you can just use the letters and numbers. Ultimately land on the letters and numbers, but whatever you need to do to get there is fine. And then when you've got configurations shown to the people around you, see if you've got the same ones, and if not, talk about what the differences might be. Yeah. Right. Yeah.
Good guess. Probably D is that L is 2. L equals 2 can exist where N equals 2. It doesn't exist where N equals 3. So if it were possible to have these, they would be X, but since it's not, it's that 3, we can go to the S first. So that's
So for those of you who got to the second one, to P, what do you do after you fill up the 2P? Where do you go next? Yeah, 3S. So you're going to go up an N level because you can't have a D in number 2. That violates the quantum number rule. So you go up to number 3. You start back on the S again because that's going to be the lowest energy, the lowest L value. And go up from there. Yeah. Yep. Mm-hmm. So that's a yeah, that's it. That is what? Well, it can't be if there's not a number. So yeah. No, because how many electrons can fit in 3s? Right. So then now you go to the next. Think about what that might be. Well, no, we just don't know. All right, let's look at the first couple here, and then we'll think about what those other things mean. So it's always a good idea to just write down the total number of electrons here. So nitrogen's got 7 electrons, and E with a little line, a little negative sign is often used for electron. Phosphorus is going to have 15. Chlorine 17. And then what do we do about the ions? Do you remember from back in whenever we talked about that? How many electrons does sodium ion have? 10, because it's got 11 as a neutral atom. It's a positive ion, so we take one away. So 10 electrons. And O2 minus, also 10 electrons. Because we had 8 as a negative ion, and then you add 2 more and you get 10. Okay, so now we can set up boxes or however you want to do that. We can just do like lines. So we can talk about the 1s, whoops, the 2s, the 3 different orbitals in the 2p, and start filling them up. So we go 1, 2, 3, 4, 5, 6, 7. And so that would be the configuration for nitrogen. We would write it as 1s2, 2s2, 2p3. The only problem with that written way, that last way we do it, is it doesn't explicitly say whether the electrons are paired or not. So you have to know some things about electrons and about orbitals to realize that those would be unpaired electrons. And there's some physical consequences of that we'll talk about in a little bit. So phosphorus is going to have 15 electrons. So we start the same way. The 1s, the 2s, the 2p, and we'll fill those up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we need 5 more electrons. So we need another orbital. We can't put the d in there because that would be L equals 2, and we can't have L equals 2 in the N equals 2 level. So we have to jump up to the next level, level 3. We're going to start with the 3s, and then the 3p. 1, 2, 3, 4, 5 more. So that electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Chlorine's just 2 over, so we're going to have 2 more electrons there. So very similar setup. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 1 spot left open for an electron, which gives us 1s2, 2s2, 2p6, 3s2, 3p5. Down to the ions, nothing special here. We had to use the fact that they're ions to figure out the number of electrons, but the configuration goes the same. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And oxygen, having the same number of electrons, is going to have the exact same electron configuration. So those are both going to be 1s2, 2s2, 2p6. Now, do you notice something special about that, about those configurations? They're all full. That's a special situation because it's extremely stable. So we call this noble gas configuration. Because it's the same configuration as whatever noble gas is at the end of the row. And that's actually the explanation for why the various columns that we say always form a particular ion. Well, that's why, because if oxygen forms a 2- ion, it achieves noble gas configuration, which is especially stable. If chlorine takes 1 electron, it makes noble gas configuration, again, very stable, so it's a 1- ion. So that's where that stuff comes from. The other way that we use this is to make it kind of a shorthand. These electron configurations are getting pretty big, and when we get into the bottom of the periodic table, they're going to get even bigger. So one way that we do that is by actually starting at the noble gas, the closest noble gas, and counting from there. So instead of calling this 1s2, 2s2, 2p6, we could actually call this the neon configuration. And so we put neon in brackets to show that that's basically the same, or it is the same as just the neon configuration. And then when we do other atoms that aren't exactly noble gas configuration, we can still use the nearest noble gas to write that. So like phosphorus and chlorine above, this is the same as saying, okay, we're going to start with neon and then count from there. So we're going to start with neon, which is 1s2, 2s2, 2p6, and then add the 3s2 and the 3p3. So I guess it's not actually the same, it's just equal to. And then over here we could do the same thing. This is neon 3s2, 3p5.
Why wouldn't neon be the closest to phosphorus?
Because you can't subtract from it, so you have to go to like the closest previous one. Yeah, because argon is closer, but you can't say argon minus 2 electrons. You say neon and then what it has from there. Okay, so what happens when we go on? We'll talk about the transition metals and then we'll take a break. So after argon, we've filled up the 2s, the 1s, the 2s, the 2p, the 3s, and the 3p. So where do we go from there? Let's look at it. Let's make our boxes. So we got our 1s, 2s, 2p, 3s, and 3p. So what's next? Yeah, well, we have to kind of make a decision here, right? And I heard both options here. We're in the n equals 3 shell, so we can go to the d in this case because we've got d orbitals, or we can skip the d's and go into the 4s. So we'll talk about what happens. But let's write down those 3 d's. How many d orbitals are there? 5, because it's L equals 2. So that means ML is -2, -1, 0, 1, or 2. So there's our 3D. And then we'll just keep going here with the 4s for a minute. And we can keep going from there. All right, so let's look at an atom like potassium. So potassium's number 19, the one that comes after argon. So we're going to fill up all the argon ones first, which is through the 3p. And then where does that next electron go? Well, it would make most sense for it to go in the 3d. But in fact, what happens in that final atom is it goes in the 4s instead. So that the configuration for potassium starts with argon, which is this. And then we add 4s1. So not 3d. But here's where there's a mistake in the book, and in many books, actually. It's a really common misconception. The book talks about it like this. They say that, well, okay, after the 3p, the 4s is actually lower in energy than the 3d. So you fill up the 4s first, and then the 3d. And that's actually not true. The 4s is at a higher energy than the 3d. It makes more sense chemically to look at it like this. And to say instead that those first couple electrons get promoted up to the 4s. So it's not that the 4s is lower in energy. It's that a couple electrons from the 3d are being promoted up to the 4s. Because of a lot of things that are going on in the atom that we don't need to get into.
Because complicated quantum things, I'm guessing.
Complicated quantum things. Yeah, we'll leave it at that. Something called spin orbit coupling and a couple other things. So we don't have anything in the 3D. We instead go to the 4s. And in fact, this happens for 2 electrons, both potassium and calcium. And it's not until we get to the third one in that row, scandium, that we start to fill up the 3D. So the electrons would go into the D, but 2 of them get bumped up into the S. And then we start counting up like normal. So titanium, the next one over. But here's why it's important to think about it this way rather than the way that the book has it. Because when we make ions, let's take the 2+ ion of titanium. So that's going to be titanium with 2 fewer electrons. If we just say that the 4s is a lower energy than the 3d, then we would take those 2 electrons from the 3d and we'd have the same configuration as calcium. But that's not what happens. The configuration of titanium 2+ is missing the 4s electrons. So it's those promoted electrons that get taken out first. And that makes sense because if the 4s is higher than the 3d, then those are the electrons that should come out first. And that's what happens. So if you keep the ordering the way it makes sense and just think about 2 electrons from the 3d get bumped up to the 4s, but those 2 are going to come out first when we make an ion. Okay. So that's a weird thing that happens with the transition metals in the middle. If you haven't noticed it already, take a look at the periodic table. The shapes of these blocks exactly mirror these orbitals. So 1a and 2a are known as the s block. Those are atoms where the outermost electrons are in the s orbitals. And there's 2 of them because you can get a maximum of 2 electrons in an s orbital. And the s orbitals total is just 1. If you look over on the right, boron through neon, that whole block, that's called the p block elements. Because there's 6 columns for the 6 electrons that go in the p orbitals. And so you can figure out an electron configuration just by looking at an atom's position. So let's go back to phosphorus, number 15. We could say that's got 15 electrons and count them all up. Or we could say, all right, it's in the 3rd row, and it's the 3rd one in the p block, right? Aluminum, silicon, phosphorus, the 3rd one in the p block. So it must go up to 3s2, 3p3, 3rd one in the p block. So that's another way of thinking about that. And then if we look down at the transition metals in the middle, how many do you think there's, without counting, how many do you think there's across from scandium to zinc? If you were to guess. Well, how many t orbitals are there? 5, so how many electrons can be in the d? 10. So you think there's probably 10 transition metal rows or columns? Yeah, so there is. So you can look at the position across there to see how many d electrons they're going to have. All right, so then have we talked about everything? One last thing.
Like the stuff in the very bottom.
Yeah, what's going on with the stuff in the very bottom?
Should that technically be like expanding?
Yeah, so it actually goes in between 57. See where 57 is, where the little star is? So we should really split that whole periodic table apart and stick those 2 things right in there, but that would make for a really awkward, long presentation. So we put them down below. But they actually go right in there. So what's going on with those elements? What's special about them? What? The F block. Why are those called the F block?
Where's the E block?
There's no E block.
Then why is there an F? Like what's going on?
Yeah, exactly. What's going on?
SPDF.
Because it goes SPDF. So those are the ones that have L equals 3, the F orbitals. They're going to have electrons in F orbitals. All right, so rather than count all these out over and over again, let's grab a chart from the book so we can have it in the notes and talk about some of the weirder ones that are going to come up here. Whoops. Go too far. Yeah. Okay, this is going to be kind of small and hard to see, but it's in the notes. You can pull it up on your computer if you want. So here are all the electron configurations, the outermost electron configurations of all the elements in the periodic table. So they're not showing the noble gas part. But you'll notice it mostly follows the rules that we've been talking about with a few exceptions. There's a couple important exceptions in the first row. Chromium and copper. If you can see that, you can probably see, their configurations, instead of being 4s2 and then however many in D, actually it's 4s1. So the way we explain that is those are almost at the halfway point. So they would be D4 if we promoted 2 up to the s. But there's another special situation where having a half-full orbital is stable. And so that's enough of a stabilizing factor to prevent that second electron from being bumped up into the s, into the 4s. And it actually stays in the 3d. So chromium ends up being 4s1, 3d5. Copper ends up being 4s1, 3d10. And that actually holds for the elements just below them as well, in the 5 and 4. Once you get down below the third level, things get a little less predictable. So you don't need to memorize all of these. Like you'll notice, niobium has a little bit of a different one. So does ruthenium. So does palladium, where actually nothing gets promoted up because of the full orbital makes it especially stable as well. So there's various things going on here, and you don't have to memorize all the different exceptions. The reason for that is there's very little energy difference between being promoted versus not. So whenever there's other factors that can come in, that can pretty easily compensate for that. So you see some of those differences. And then down in the Fs, they also get kind of messed up with sometimes there's some that stay in the D, sometimes there's some that get promoted up to the D, sometimes they all end up in the F. Again, a lot of different things going on there. So you don't have to know all these exceptions. You should know these two, because those are important exceptions for important first row elements. But all the rest of the bottom, don't worry about.
Because those 2 elements you use a fair amount and like. So
Yeah, right.
Like the rest, like we don't really care about.
And there's other things, and you could always look stuff up if you really need to know the ground state electron configuration for some of these other ones.
The electron state of palladium.
Yeah, the important thing is that you know how to construct the electron configuration. And so even if I asked you one of the bottom ones, like on a quiz or an exam, I would expect you to write the predictable one, the one that you would predict based on the rules that we talked about, not know every little exception and idiosyncrasy of the periodic table. Okay, let's stop there and take a break. And we'll come back and kind of talk about the consequences of this, how we can use this to explain chemistry, to explain what happens in the physical world.
That's
All
a
right,
bold
let's
statement.
continue. It's a bold statement. Well, okay, so everybody always wants to know, what's the answer? You know, what's the answer on the exam? What's the answer on the quiz? Well, in this chapter, in the second half of this chapter, the answer is almost always something to do with effective nuclear charge. Now, you can't just write that down and expect to, you know, get it totally right, but it should give you a way to think about the answer. And if you're not talking about effective nuclear charge, then chances are you're not on the right track. So let's talk about what this is and what it means, and then how we use it in basically every situation in the last half of this chapter. Start with a picture again. And actually, they talk about this at the beginning of this chapter. Get there yet? Here. Okay. So we established that electrons closer to the nucleus are generally at a lower energy because of the interaction with the nucleus. The positive and the negative charges attracting each other. But there's something else going on too, and that's that there's other electrons around. So electrons that are further away from the nucleus and have other electrons in between them experience something called shielding. And shielding is the ability for other negatively charged electrons to shield or to protect those outer electrons from feeling that full pull of the nucleus. So it's not just that they're farther away, but it's also that there's other electrons in the middle that are preventing them from feeling that full pull. And so that's why we talk about this term effective nuclear charge, which is what's going on right here. So the nucleus in this particular example, this is a lithium atom. The nucleus in this particular example has a 3+ charge. But that electron that's outside those other two only really experiences a charge of about +1. Because we could say one of those charges is used up with one of those internal electrons and the other one's used up with the other internal electron. So the one on the outside is only feeling one of those 3 positive charges. And that's a little bit simplistic way of thinking about it, but it actually works. So that's the effective nuclear charge. The effective nuclear charge for that particular electron is 1. Now, if instead we have an electron that penetrates deeply into the cloud toward the nucleus, that electron is now experiencing that full 3+ charge because it's really close to the nucleus and there's nothing else around it. So even if it were further away from the nucleus, the fact that there's nothing in between it and the nucleus means that it's going to experience that full 3+ charge. So that's the higher effective nuclear charge. So that's what we call the effective nuclear charge. This explains what we've talked about so far, the ordering of the orbitals. And I'm not going to pull these in, but we can just look at them. Okay. Open this up or? No, guess not. So here's a graph of total radial probability versus atomic radius. So what this is showing is what is the probability of an electron being at that distance from the nucleus. The far left is the nucleus, so that's 0 because an electron can't be in the nucleus. But then where is it going to be outside of that? So the blue one, or the one that's really kind of tall, is the 1s orbital, which means the higher probability for an electron in a 1s orbital is that it's closer to the nucleus. As we go to the 2s, we get a little bit further away. As we go to the 2p, and actually the maximum probability is a little bit closer. But because of that extra penetration of the 2s, the fact that there's a little lobe of the 2s that's way in close to the nucleus, that means that the overall effective nuclear charge of an electron in the 2s is going to be greater than in the 2p. Because on average, it can be a little bit closer to the nucleus. And I don't know if is there a graph where they put that all together? No, they just kind of look at some other ones. But that's where they get this idea of this ordering, that the s is going to have that extra penetration close to the nucleus. Okay, so that explains the ordering. How does it explain all these different properties that we're going to talk about now, like size and ionization energy and stuff like that? Let's define another term here. The valence electrons are going to be all the electrons that have the highest n. So the highest n level. So if we go back up to one of our configurations here, we'll jump back down a second. Like we say, let's look back at when we see the whole thing. So we see potassium, 1s2, 2s2, 2p6, 3s2, 3p3. All those electrons, the 3s2 and the 3p3, we're going to call the valence electrons for the highest n level. So it's not just the 3p, it's everything in the highest n level. What do you think is special about all the electrons in the highest n level with respect to effective nuclear charge?
They have the least.
Yeah, they're going to have the lowest, is that what you're going to say?
Oh, no.
Okay, go
I
ahead.
was going to say they combine.
They combine with other ones, yep. So why is that? It's because, as you said, those are the ones with the lowest effective nuclear charge.
So they can bond with other electrons because they are more easily able to like escape from the nucleus or something like that.
Right. So it's not just that they're further away. It's more that there's lots of other electrons in between them and the nucleus that give them a lower effective nuclear charge and allow them to, we could say, escape that pull. Or there's just less of a electrostatic force between the nucleus and those outermost electrons. So those are the electrons that are most important to the chemistry of the atom, to the actually doing stuff, losing electrons, gaining electrons, sharing electrons, which we'll talk about more in chapter 9 on Thursday. The other electrons are called the core electrons. So if you had, let's say, sulfur, now we can write that configuration much more quickly because we can see that it's in the 4th position of the P block on the 3rd row. And I'm going to write the whole thing out just so we can see all those electrons. Whoops, sorry. P6, 3s2, 3p4. So that means that all of the electrons in the n equals 3 level are going to be called the valence electrons. So we'll say that this has 6 valence electrons. And all the rest of the electrons are called the core electrons. So that's 10 core electrons. Notice that the core electrons are defined based on the valence electrons and not the other way around. So if you have an atom with very few electrons like helium, only has 2 electrons. Both of those electrons are in the 1s2. Those are both called valence electrons. And the other ones are called the core electrons. Or, I'm sorry, and there are no core electrons. Here. So the outermost or the highest n level are going to be the valence electrons. All right, determining the number of valence electrons that an atom has is really important. So there's a nice shortcut for that. Does anybody know what it is?
Would it be the we were doing like those that orbital thing right there?
It's even simpler than that.
So that, okay.
Yeah. It has to do with the periodic table. It goes what? Yeah, it goes across the top. And if you look at the column labels, especially the old A and B way of doing it, so like sulfur, how many valence electrons did we come up with? 6, right? Well, sulfur is in the group 6A. So all of the members of that group are going to have 6 valence electrons in their neutral state. If you have a periodic table that only has the new numbers, the 1 through 18, you can just use that second digit and say all those in column 16 have 6 valence electrons. All those in column 15 have 5 valence electrons, and so on. It breaks down in the middle. That's why those are the B's. The transition metals have a different way of thinking of valence electrons, and in fact, it's not even really that important to think about valence electrons in the transition metals. We count electrons in a little bit different way with those. But for the other ones on the other sides, that works quite nicely. So we can do that. All right. So let's look at how this idea of effective nuclear charge and valence electrons can explain some what we call periodic trends or periodic properties. So periodic trends are just like what happens as you go across the periodic table, what happens as you go up or down the periodic table. Can we predict what's going to happen with various properties? And that's really useful because then we don't have to be constantly looking up numbers. So the first one we're going to look at is atomic radius. So how big is an atom? You can look up tables and find out exactly how big all the different atoms are in picometers, but you rarely need to know the exact number. More often, you just need to know, is this one bigger or is this one bigger? And so we can talk about how we can figure that out by thinking about effective nuclear charge. So before we look at a graph of which ones are bigger than others, what would you think, and we'll start with the easier one, as you go from top to bottom in the periodic table, do you think that atomic size increases or decreases? So as you go from the top, the elements in the top, down to the elements on the bottom, would you expect the size to increase or decrease? Increase. Almost everybody said that. That's true. Why? How'd you know?
There's more stuff.
More stuff? Okay, like what kind of stuff?
Protons,
Protons, but protons don't
neutrons.
take up much size, right? Because we're talking about radius, not mass.
More electrons.
More electrons is really what's important. And even more important than that is more levels of electrons. Because every time you go up to a new n level, you now have a larger radius because those new electrons are further away from the nucleus because of their radial probability. So in general, we would say atomic radius increases from top to bottom Oh, there is another picture of effective nuclear charge. Okay, anyway, we'll get to that. Because of if we want to say that specifically, or correctly, we would say n level. So if you plug those different values for as you increase the value of n in the wave function, you get a probability distribution that is further away from the nucleus. And so another way of saying that is the electrons in higher n levels, higher quantum levels, are further away from the nucleus. And that makes the size bigger. Okay, so now what happens if we go from left to right on the periodic table? So if you're going across the row, let's take like row 2. So you're going across row 2 from lithium to neon, going from 3 to 10. The size increase, decrease, or stay about the same. So now we're talking about staying within the same n level. What happens to the size? It's a little trickier. You're going to go with increase. Why? More electrons. Makes sense. Anybody else? Ideas? Let's look at the actual data on this one. It's on page 353 in the book. So here's radius versus atomic number. Okay. So the atomic number is on the bottom, which just means as we go from left to right, we're going across the periodic table and then to the next row, the next row, the next row. And there's radius on top. So if you look down a column, like the very tops of those peaks, lithium, sodium, potassium, rubidium, cesium, that's what we just talked about. That radius is going up as you go down. What happens as you go across from lithium to neon?
Yeah.
The radius is going down. In fact, it's dropping quite a bit, and then it kind of goes, but it's basically going down as you go across. So that's maybe counterintuitive. Why, if you're adding more electrons, why should the size be going down? How does that make sense?
Are you really adding any more levels though?
Are you?
I don't think so.
What do you think? Yeah, exactly, right. So there's no, so we're within the same n level, which means our atomic radius, yeah, like the radial distribution changes a little from S to P, but not a whole lot. The biggest change here is that we've got more electrons and more protons in approximately the same level. So the effective nuclear charge on those is going up. Remember how we calculate nuclear charge? There's another picture on this part in this section of the book too, so we can look at this too. So the way we calculate effective nuclear charge is, let's say we're looking at a valence electron like the 2s1 here in lithium. So we subtract any electrons that are inside of it, that are on lower n levels. So let's look at, okay, we'll start with lithium. So lithium is 3 electrons, 1 valence electron, and 2 core electrons, and a nucleus of +3. So you take that +3 nucleus, you subtract the 2 electrons, and that means that the valence electrons are feeling about a +1 effective nuclear charge. Let's compare that to neon all the way on the other side of that row. So now how many valence electrons does neon have?
0.
Well, remember the highest n level are the electrons. So it can't really be 0. So we would say 8. 8, because it's in 8A. So 8 valence electrons at the 2p2 and the 2p6. So you got 8 valence electrons, still 2 core electrons. And what's the charge of the nucleus in a neon atom? 10 plus. So you got 10 plus nucleus, 2 core electrons, which means the valence electrons are feeling an 8 plus effective nuclear charge compared to the 1 plus in lithium. So that's why we have this contraction across the row. There's a higher effective nuclear charge by more protons, more electrons, pulling each other together. Let's emphasize this here because it is a little bit counterintuitive at first. And again, answer to everything. We should also note the symbol for effective nuclear charge is ZEFF. So Z,
Zeph.
Zeph. Z means charge, and so it's the effective charge, the effective nuclear charge. All right. So that gives us our general trends. Now remember, we're talking about general trends here. So there's always little exceptions, little other factors that are going on because it's nature and it's a little messy. But we can point to these general trends. And we're going to talk about some of the exceptions and how we can discuss some of that as well. But you see the same kind of thing going on in the transition elements and in the lanthanides as well. So when you have these electrons and protons being added to elements without the size really increasing much, or without the shell level increasing, you see everything kind of being pulled together. And so the size goes down. All right. What happens if instead of atoms, we're talking about ions? So the radius of ions, or the radii of ions. What do you think? So now we have a good framework, a good theory of understanding what causes these trends and how they work. And it's this effective nuclear charge idea. So thinking in that way, thinking about effective nuclear charge, what happens if you take an electron away from an atom? What happens to the size? Does it go down or does it go up if you take an electron away?
Goes up.
The size goes up so it gets bigger?
No, it gets smaller.
It gets smaller. Why does it get smaller if you take an electron away?
Wait,
Anybody else want to jump in? Yeah, go ahead. Yeah, certainly that would matter. So if you let's say had sodium, which only has one valence electron, if you took that electron away, you'd be jumping down a whole n level. So that would certainly do what to the size? Decreasing. Now instead of being at the n equals 3 level, you're at the n equals 2 level. What if you lose an electron but you don't go down in level? So let's say, I don't know, like magnesium, you lose 1 electron instead of 2. So magnesium plus 1, which doesn't really exist, but
Let's go with it.
would it go down, still go down in size, or would it stay the same? Or go up?
Just from the chart they showed before, it makes sense that it would go up.
Okay, well think about what's going on. How is the effective nuclear charge changing when you lose a valence electron? If there are other valence electrons also still there?
No.
Not really, no. But what is happening is you now have fewer electrons that are feeling that positive charge. So the net effect of that is because the effective nuclear charge is spread out over fewer electrons, there is going to be that contraction. So you end up getting smaller. So positive ions are always smaller. Positive ions are always smaller than their neutral atoms. And the more positive charge you have, the smaller it gets yet. So there's a neat chart in the book that shows this. Let me grab that here. Oh, that's really small. Well, let's just look at a couple of them. We don't need the whole chart. So just take a look at these, for instance. So going across row 2, lithium, beryllium, boron. We know that those sizes go down a bit anyway as you go across because of the stuff we've just been talking about. But now look at their ions. Their ions also decrease in size, but they're way smaller than the neutral atoms, like way smaller. So that charge effect is much, much bigger than the other effects we talked about before, than like the trends. Same thing in the next row. The cations are much, much, much smaller. So if you're comparing size between an atom and an ion, a neutral atom and an ion, you can always make a pretty good bet that that positive ion is going to be smaller. That only really starts to break down when you talk about big ions versus small atoms, but that would be a really tricky question. So what do you think happens with anions then?
They get bigger.
Yeah. So same thing, we'll look at some neutral negative ions here. Okay. Take a look between oxygen and fluorine. Okay, same shell, but the 2 minus oxygen is going to be a bit bigger than the 1 minus fluorine. The 2 minus sulfur is going to be a bit bigger than the 1 minus fluorine. And the important part of this is all of those are much bigger than their neutral counterparts. So there's always a contraction going across, but having a negative charge means you're adding electrons, means the effective nuclear charge goes down, and so that can expand and become much bigger. Notice here, unlike the other ones that we just looked at, unlike the cations, when you're adding electrons, you're not adding them to a new shell. Like when oxygen goes from neutral to 2 minus, those 2 electrons are going into the 2p. So they're staying in the same n level. But because there's now more electrons in that valence shell for the same nuclear charge, they're not being held as tightly. So the number of electrons outweigh the charge in the nucleus, so they can expand a little bit. Okay, so now we've got 2 good trends that we can explain using effective nuclear charge, the atomic radius and the ionic radius. And we're going to look at a couple more, and that'll be it. Let's keep our numbering scheme here. So we did 1, we did 2. So let's look at 3. Ionization energy. Ionization energy is a neat property to look at because it really makes us kind of tests if we understand what's going on in the orbitals, what's going on with the electrons, and if we can really talk about effective nuclear charge. So what's ionization energy? Ionization energy is the energy required to remove an electron from an atom. So based on what we just talked about in the beginning of class, is this an exothermic process or an endothermic process? Exo, endo. So the system here is going to be the atom. So if there's energy required to remove that electron, does that mean the electron's being put in or being taken out? It's actually being put in this case. So you have to put, energy required means you're putting in the energy to knock the electron out.
So it's endothermic.
So it's endothermic. So if you have a gaseous sodium ion, you add energy and you make sodium plus an electron. Sometimes we don't think about it this way because we think about like atoms wanting to lose electron. We use that verb to want as though they have agency. But really it takes electrons. You have to force an electron, or energy. You have to force an electron out of an atom. The ones that seem like they want to lose electrons, it's more because of other stuff that's happening in that process. But you actually it's always required to put energy in to remove an electron. All right. So that is called the ionization energy. And this is specifically called the first ionization energy. So for example, for this one, the value is 496 kilojoules per mole. So for every mole of sodium ions, it takes 496 kilojoules to remove an electron. There are also second and third ionization energies, which are the energies to remove successive electrons. So you removed one, then you can remove another, then you can remove another. We'll talk about those in a minute. But let's first just talk about trends in the first ionization energy. And again, let's see if we can figure out the trend before we actually look at it. So what do you think as we go down the periodic table? Let's start with that one again. As you go down the periodic table, does it require more or less energy to remove one electron? More. Why? Because it's more stable? How is it more stable? Okay, we're going down. We're going down. So we'll get to that one in a second. So if we're going down, same answer. Requires more.
So the further down you go, like from hydrogen to cesium.
Yeah.
Like,
More or less
I would
energy
say
to
take
remove an
less.
electron. Why?
because the effective nuclear charge for that atom would be lower.
Yeah. So the overall nuclear charge is lower. It's not the effective nuclear charge. It's more the overall because they're further away from the nucleus.
Yeah.
So it's easier to remove the electrons further away from the nucleus. Okay. So now let's talk about going across, and then we'll check if we're right here. But going across, so you want to go back to what you were saying before? Yeah. So we've got stable is kind of a broad word, but you're right. So let's say the effective what happens to the effective nuclear charge as we go across the periodic table? Does it get greater or does it get smaller as you go from left to right? It's greater, right? Because you've got more protons for the same shell. So the pull is greater on those electrons. So that's going to lead to it being harder to remove those electrons. Right? See that? If the pull is greater from the nucleus, then it's harder to remove those electrons. So let's see if that's reflected in the trends that are measured. We can use the language harder or easier to remove electrons if that helps. So we can draw on it. Okay, so here are the first ionization energies for the elements going up in atomic number just like before. And so we see that our predicted trends are actually right. That as you go down the periodic table, which would be like just the red ones, the noble gases, or just the blue ones, the alkali metals on the bottom, that the ionization energy goes down, which means it's easier to take off the electrons as you go from top to bottom. And then going across the periodic table, it gets harder to take out the electrons, again, because of that effective nuclear charge. So those are the general trends. Now with this one, let's look at some of those exceptions and see if we can justify them. So if you look at this, if you try to think about patterns here, you go like jump up here from hydrogen to helium. Then it goes up, down, down, up. Then up, down, down, up. Then up, down, down, up. Then up, down, up, about the same, up. So other than the transition elements, which get a little weird, when we see some sort of like random seeming variation, that's something we can say, okay, well, there's just some special stuff going on. But if we see this regular pattern where it always seems to go up from 1 to 2, then down, then up 2 more, then down, and then up for the rest. And it always seems to fit that. So can we explain that? Why is that happening every time? Let's just look at that first blip. So in pretty much every one, you start from the alkali metal, you go up to the next one, and then there's a drop down before you get to the third one. What's happening there? Could you make a guess? Why would it be easier to remove the third electron than the second electron? If the general trend is that it's always harder going across, why is it easier to remove the third one than the second one? Yeah, you see that? So like in the second row, you got lithium here, you got beryllium, and then all of a sudden it's easier to remove boron's first electron than beryllium's.
Because the second one is a complete filled s orbital, and the third one is a unfilled first orbital.
Yeah, so let's look at the valence electrons here. So lithium's valence electron is going to be the 2s electron. Beryllium's going to be the second 2s electron. And then boron is going to be removing a p electron. Now we know p orbitals are a little bit further away from the nucleus on average than s orbitals. So removing a p electron is going to be just a little bit easier than removing that full s electron. There's also, so that explains that first blip, and that's going to happen all the way across because we always have that happening. So if we've got S, S1, S2, and then P1, those are the electrons that are being removed. S1, S2, P1. S1, S2, P1. So that removing that first P electron is always easier than removing the second S electron. So there's two forces at play there. One is the P being further away. Second is, same thing when we were counting up electrons, having half full or totally full orbitals is an especially stable situation. So that full S is going to be a little bit harder to remove just one than the P that comes after. Okay, so that helps us explain that first blip. How do you explain the second blip? Where is it and what's going on there? So this time, we're not going to talk through it together. I want you to talk through it with the people at your table and see if you can come up for an explanation as to why it's easier to remove the 5th electron than the 4th electron. Or sorry, the 6th electron than the 5th electron.
We're going to D5 and D6.
Anybody come up with some reasons? Talk about it. You get a reason?
I don't think a good reason.
You don't think a good reason? It's okay. A reason? You wanna? No? Anybody else? You got something? Okay.
Because like if you have a D, I think it's similar to like the P3 you see up there, where it's like if like you find it's easier to get a D6 and D5, so it's like so if you have a D5 orbital, there's 5 unpaired electrons in each other. Once you enter the D6, one of those unpaired would have a full one.
Yeah.
And it's just easier to like it's just harder to rip off a one of those than the other.
Yeah. So I think you're on the right track. Let's look at what those. Anybody else want to add to that, or do you have other ideas? See, let's look at what those are. So if we've got, let's just look at the first one, the first or the second row for now. So we've got lithium, then beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine. So the weird thing that's happening here is between nitrogen and oxygen. So let's look at the difference in those configurations. Nitrogen, let's look at just the valences. So here's the 2s and the 2p. So we've got 5 valence electrons. That looks like this. Oxygen, same thing, but 6 valence electrons. So what the graph is telling us is that it's a little bit easier to take out this electron, this last one on oxygen, than it is one of those on nitrogen. And so I think you're right to point to the spin pairing energy. We said that because electrons repel each other, there's a little bit of a cost associated with putting 2 electrons in the same orbital. So what's happening there is that oxygen final electron is a little bit less stable or a little bit higher energy than would otherwise be expected because it's paired up. Whereas nitrogen's p electrons are all unpaired. So we've got a little bit of energy cost associated with pairing that electron, which makes it a little bit easier to take off, a little bit easier to tear away. And so that's also repeated here and here and here, and the effect becomes less and less as you go down the periodic table, because there's other things that start becoming more important. But that general trend holds through those p electrons. So those are kind of the 2 exceptions here, right here and here. Any questions about those? So that's trends in first ionization energies. Let's look at subsequent ionization energies. I want to show you this graph from the book and see if we can explain what's going on here. You can find it. Jump down to the beginning for some reason. Okay. Take a look at this graph. We've got sodium and magnesium, and we're looking at the energies of the first, second, and third ionization. So that means the energy it takes to take off one electron, then the energy it takes to take off the second electron, not both, but just the second one, and then the energy it takes to take off just the third one. So it's not cumulative, it's the energy that it takes for each subsequent ionization. So for sodium, we see a relatively low first ionization, and then all of a sudden, a huge jump into the second ionization. In magnesium, we see a relatively low first ionization, a little bit of a jump in the second ionization, and then a huge jump in the third ionization. So what's going on there? What's happening in those huge jumps? The what? Yeah, they're leaving noble gas configuration. Another way of saying that is we're no longer taking out valence electrons, we're taking out core electrons. So this one here is the valence electron, the 3s1. But this one here now, it's starting to take out the 2p, which is the core electrons. So there's going to be a whole lot more energy there because those core electrons have a much higher effective nuclear charge. So they're being held much more tightly by the nucleus. It takes a lot more energy. Why is magnesium's pattern a little bit different? Why does it go low, low, and before the jump? Why are there two kind of reasonable ionization energies before the jump to the huge one? Yeah, right, exactly. Magnesium has 2 valence electrons instead of just 1. So you get 2 reasonable valence ionizations before you start taking out those core electrons. We can actually use ionization energy then to predict what an ion is, or what an atom is. Let me show you an example of that in the book here. Take a look at this problem. This is something that comes up pretty commonly when talking about these things. Consider this set of ionization energies. To which third period element do these ionization values belong? So which element in the third period, that's the third row, has those ionization energies for first through fourth ionization? How can you tell? How can we think about this? You think it's aluminum?
Yeah.
Why?
Because if you go through this, you see that aluminum takes three loose classes of electrons to get into noble gas state.
Mm-hmm.
And then with the fourth one, it loses noble gas state, and you have a very high increase in ionization energy.
Yes, right. So thank you. So we can see here there's a big jump right there. There's like 3 reasonable ionizations and then a really huge one. So that tells us that these must all be valence electrons. And this must be a core electron. So we can ask ourselves which element in the third period can lose 3 valence electrons before losing a core electron. And the only answer there is aluminum, because that's the one with 3 valence electrons. So it's in column 3A. It can lose 3 electrons, but then when it loses that fourth one, that's coming out of the core. So that's going to be a much, much higher ionization energy. So you see how that works? All right. So another quantity that kind of goes along with ionization energy is electron affinity. So this would be 4 now. Electron affinity is the energy change when an atom gains an electron. Notice I have a more general definition here. Instead of saying the energy required or the energy released, I just say the energy change. And that's because atoms can have both positive and negative electron affinities, depending on the atom. So we're talking about something like this. Chlorine gains an electron and becomes an ion in the gas state. And there's some energy associated with that. For chlorine specifically, the change in energy here, which is called the electron affinity, is negative 346 kilojoules per mole. So the fact that it's negative tells us what? direction is the electron or is the energy moving in this reaction? Is this process?
It's moving to the
Yeah.
to the normal element. I think.
Well, let's talk about it in terms of like.
Towards like
It's
Yeah. Well, so let's use the terms from the energy stuff. Is it exothermic or endothermic? It's exothermic, right? The negative energy means that the chlorine atom is releasing its energy to the surroundings in this process. So this is a process that releases energy. If we look at a graph of electron affinities, oops, still ionization energies. Here are some electron affinities. Positive electron affinities we usually don't worry about. We just kind of say, okay, those are atoms that have very, very low magnitude of electron affinities. So you'll see here it just says greater than 0. All metals pretty much have either very small magnitude or greater than 0 electron affinities, which means they don't want to gain electrons. So the general trend here does what, if you look at those numbers? Going across, what is the general trend in electron affinities? To go up or down in overall. And we should say up or down, we're talking about magnitude. So like more negative would be up. So going from left to right, in general, is the trend that the energy magnitude increases or decreases? What do you think? So it definitely kind of goes a little wacky, but the general trend is from left to right for it to be going up in magnitude. In other words, as you go from left to right, the atoms release more energy when they gain an electron. They want to become negative. And we can remember this trend just by looking at the periodic table, that we know all the negative ions are over on the right, positive ions are over on the left in general. So that tells us that, okay, probably the ones on the right are going to be more likely to gain an electron. That's how we can remember that trend. Now there's one really clear exception here, and that's right in the middle. So you go more negative, drop to positive, and then more negative and more negative. So what's going on there? Anybody explain what's happening here that makes those atoms less likely to gain an electron than the ones on either side? Why don't we follow the trend right there? What's happening? What do you have to do when nitrogen gains an electron? What's happening to the electrons? Well, that's always the case when you gain an electron. What's special about nitrogen and the others in its row? Yeah, one of them's going to have to pair up. So nitrogen has 3 unpaired electrons in its p orbitals. So if it gains another electron, it has to pair those up. And if it pairs those up, we know there's a energy cost associated with that. So that's why that electron affinity is, we would say, much lower, which means that it's positive. It doesn't want that electron. And that holds for everything else in its group, that there's a dip downward at that position. Why don't the noble gases gain electrons?
Because they're done. They have everything they want.
Okay, they're like in chemical terms, they're stable, but so where would that next electron have to go? Have to go to a whole new quantum level, yeah, a whole new shell. So you're talking about an extremely low effective nuclear charge, and that's really not going to happen. So it's unlikely that an atom will make an ion where it has to gain an electron in a new quantum level, in a new shell. Okay. You can put those together in something called metallic character. We don't have to mess with that too much, but you know where the metals and the nonmetals are on the periodic table, right? We've talked about that before. Okay. So what do you think the trend is for metallic character? Which direction do things behave more like metals, left or right? It's not a trick question. Which direction do atoms behave more like metals? Yeah, left, because that's going toward the metals. Non-metals on the right and metals on the left. What about top to bottom, bottom to top? Did you guess that one? Which behave more like metals? One's closer to the bottom or one's closer to the top? What? Bottom, yeah. Same thing, you kind of look at that shape, you know, hydrogen and helium and all the non-metals in the second row are not metals. And then as you go down, you get more metallic character. Okay. So the very last thing that we should talk about is magnetism. The important thing about magnetic properties of atoms and ions, we're not talking about what's called ferromagnetism, which is the phenomenon of a solid being magnetic, like the magnets that you're talking about. We're talking about a different phenomenon called paramagnetism. Which is when atoms or molecules, but we won't get into that until chapter 10, with unpaired electrons are attracted to magnetic fields. External magnetic fields. And the opposite of that, diamagnetism. And we would say atoms with no unpaired electrons repel magnetic fields. So how can you tell if an atom has paramagnetism or diamagnetism, besides just measuring it? How can you tell from its just periodic table stuff? Yeah, you have to look at the valence electrons. The core electrons are always going to be all paired, so that's not going to make any difference. So let's say we want to look at sulfur. And we want to know if sulfur is paramagnetic or diamagnetic. It's not enough just to do the electron configuration. We have to actually draw it out and see. So we look at the valence electrons. Sulfur is going to go from neon and then have 6 valence electrons. So that's going to be the 3s and the 3p. 1, 2, 3, 4, 5, 6. So what do you think? Is that paramagnetic or diamagnetic based on the definitions? Paramagnetic, yeah? Everybody see the unpaired electrons? So those unpaired electrons tell us it's got to be paramagnetic. So does that mean that the only diamagnetic atoms are those with noble gas configuration? Can we use that as a shorthand? Careful. It seems that way for some of the p block elements, but there's a lot of other stuff going on because those definitions are very general. Any unpaired electrons or any paired electrons. So diamagnetic elements can be things like the column 2A, right? Because those have full S's, but don't have any unpaired electrons in the P's. They could also be column 2B, or number 12, the transition metals, that have no unpaired electrons because there's 10 d electrons and 2 s electrons, but the p orbitals are empty. So there are some spots in the periodic table that make diamagnetic atoms. And this becomes even more interesting when we talk about the actual compounds. We talk about molecules can be paramagnetic or diamagnetic, and we have to do some special stuff called molecular orbital theory to figure out how that works. Okay, so you feel good about some trends? Maybe a little bit? All right, let's look at, with our last 20 minutes or so, some of the types of problems that you'll see in Chapter 8. And so like the Chapter 8 homework that's up on Mastering Chemistry, this is all it is. It's like which one's bigger, which one has the higher ionization energy. So time-wise, it shouldn't take as long. It's a pretty quick homework because it lends itself to multiple choice and that kind of thing. Okay, so let's take a look at, zoom in any more of this? Let's take a look at number 70. Which is the larger species in each pair? See that? Strontium or strontium 2+? Which is larger? Yeah, why? Right, the positive ions are going to be smaller, and depending on where that is in the periodic table, it could be different. What about D? Sulfide or calcium 2+? Which one's bigger? What do you think? Sulfide, calcium 2+? Ready? Sulfide, calcium? We can hear you. They're the same? 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 Why are they the same? They both make the argon configuration, so they both have noble gas configuration, but they're not the same size. So which one's bigger? What? Sulfide, why?
Because calcium got smaller.
Calcium got smaller and sulfur got bigger? Yeah, that's correct. Yep. So let's talk about that in terms of effective nuclear charge, since that's the answer to everything. Think about the nuclei of those two atoms. So they have the same number of electrons, but sulfur has 16 protons, calcium has 20 protons. So which electrons are going to be pulled in closer? Calcium, right? Because of the more protons. So those electrons have a higher overall effective nuclear charge, whereas the sulfide ones have a lower effective nuclear charge because they actually have more electrons than protons.
So sulfur will be bigger.
So sulfur will be much bigger, even though they have the same number of electrons and the same configuration of electrons.
Because calcium has more protons, just smaller.
Right. Okay, let's look at 73. Choose the element with the higher first ionization energy from each pair. So first of all, one of the tricky things about this chapter is just keeping the question straight. What does it mean to have a higher first ionization energy? Does that mean harder to lose an electron or easier to lose an electron? Harder. So make sure you get that in your head straight first. So which of those two, bromine or bismuth, is it going to be harder to lose an electron?
Where's this?
83. Which one's harder to lose an electron? Bromine is. Why?
Because we have to go. Well, it's more because I never see a like bromine plus one ion in my life. I don't have any reason why.
Okay, so that's good. That's true, and you can certainly use your like chemical background and intuition to solve
Yeah, but I
problems like
haven't
this.
seen
But what if
those
it
yet.
asks you for why? You can't say, well, because I've never seen one. It's not a great chemical justification.
It's like,
Anybody else want to? What? Okay, it's closer to a double gas. Not in this case. No, you're right. That it's closer to noble gas configuration. What else can we say? So that would be a really good justification if they were in the same row. And it is still a justification because they're like a couple apart, right? But there's a bigger effect at play here. What's the bigger effect besides that? That's there and that's correct. But what's the bigger effect between those two that affects the ionization energy? How? It does, but why?
we
Sorry.
you say that the lower keep it correction. But it did.
Well, okay, so let's look at the thing I'm trying to get at here, I'll just say, is just the rows, right? The quantum levels. Those have the biggest effect on the ionization energy. As you go from the like n equals 4, where bromine is, down to n equals 6, where bismuth is, you have a much expanded shells. You have electrons at a much higher n level, a higher quantum level. And those are going to be much easier to ionize than the ones at the lower quantum levels. So there's two factors here that both influence that, and both point to bismuth. One is the quantum levels, and the other is the effective nuclear charge coming from the placement on the periodic table from left to right. So the fact that bromine is closer to noble gas configuration, that it's going to have a higher effective nuclear charge on those valence electrons, making them harder to ionize.
I think all the other ones say the same exact thing.
All the other ones say the same exact thing? Yeah, because there's only two reasons ever for why things have different ionization energies, right? And the only exceptions would be those weird exceptions that we talked about for pairing electrons. Okay, good. So we can do those. Let's look at something else. Yeah, we didn't take that. So what about 62 here? This isn't it. Well, let's do one of these, 63 or 64. Let's do 64. Arrange these elements in order of decreasing atomic radius. Can you see those? Cesium, antimony, sulfur, lead, and selenium. See if you can do that. Write them down in order of decreasing atomic radius, which means going from the biggest to the smallest. So you have to think about what kinds of trends affect atomic size, atomic radius, and then put them in order. All right, got some orders? So first of all, where it was good that I saw a lot of people look at the periodic table because that's how you figure this out. Where are the biggest elements in the periodic table?
Down to the left.
Down and to the left. And where are the smallest elements in the periodic table? Up and to the right. So the trends are get smaller to the right, get smaller going up. It's bigger going down, gets bigger going to the left. So if you keep those trends in mind, you can answer a lot of these types of problems. So what's the biggest out of that list? Cesium, yeah. So that's going to be our biggest. What's the next, or let's go to the other extreme then. What's the smallest in the list? Sulfur, yeah, it's the only one in the third period, and it's pretty far over to the right, so probably sulfur. Okay, so it's always easiest to do the comparisons when they're either right on top of each other or in the same period. So between sulfur and, I look around at those other ones and I say, well, sulfur and selenium are in the same group. So we know selenium's got to be bigger than sulfur because it's right underneath it. So we can put this one here. What are you going to put next?
Whatever SD is.
Antimony?
Yeah.
Yeah. So antimony goes next because it comes from a mineral called stibnite. And so it was originally, I don't know where it came, why it was changed to antimony, but
That's weird.
yeah. Okay, so then we got two more, lead and, oh no, just one more, lead. So lead's got to go in between here because it is definitely going to be bigger than antimony, but it's smaller than cesium because it's over to the right compared to cesium. So if you follow those trends, you can do these kinds of things. Now, if they had asked you to compare things that were in opposite directions, so like, let's stick with lead, let's stick with sulfur, but let's say they asked you to compare sulfur and boron. Those are in opposite directions, right? So the trend points to one for one and points to the other for the other. So you can't really do that. You gotta just look up the numbers and see. So hopefully they don't ask you that. All right, so you can do this. All right, practice up. Tomorrow, the leaf lab. So bring in leaves if you can find dry leaves. If you would like to bring in some leaves, we're measuring how much CO2 is produced by decomposing leaves. So if you have some leaves and you want to bring them in, please do so. Otherwise, just come and be ready to play with some leaves. Is it raining still again?
It's rainy today at least.
It's supposed to rain later?
No, it's supposed to stop at 4, not raining until I like 5.
Oh, okay.
Okay, so there's time to like dry up some leaves, I guess.
All right, so if you can find some dry leaves, great.
It would be
Yeah, you
okay
too.
if we dried out the leaves like overnight? Would that work?
Yeah.
Or would that
Yep.
not work?